Okay, in the same way we represent position versus time in graphs like this, where I have time and then I have position, right? And then we can also represent velocity versus time. I have time and then I have velocity. In the same way, there are acceleration versus time graph. You have time and you have acceleration. Not only that, but from the velocity versus time graph, you can extract information about the acceleration. For instance, here we have the data from the Corvette and this Chevy. So we have data, we have a t equals 0, well, they're both, the speed is 0. After 1 second, the Sonic has a speed of 3 meters per second. The Corvette has a speed of 7.5 meters per second. After 2 seconds, this is 6, this is 15. After 3 seconds, this is 9, this is 22.5, and so forth. So I can plot the two. So this one here downstairs, that's this Sonic velocity versus time graph. This one here, this is the Corvette. This one here. So if I calculate the rise, this delta V over the run, this delta T, then I get the acceleration of the Corvette. So we can then use the same type of graph that we've used so far to describe velocity, to understand the acceleration of an object if we have the velocity versus time graph. So from the velocity versus time graph, so what we do is the following. Suppose you have this graph, you're given this graph. So this is velocity up in this axis, here is time. So you have a car that the velocity starts from 0, reaches this point here, then it stays constant, and then decreases until it goes back to 0. What is the acceleration? Well, on this segment, the acceleration is the slope of the velocity versus time graph. So I would calculate the rise over the run here. And if I do that, I'm going to get a value which is equivalent to that. On this segment here, the velocity is not changing. This is constant velocity. So the acceleration is 0. So this is the acceleration on that segment. Finally, on this segment here, the velocity is decreasing. Delta V is negative. So here, delta V is positive. Here, delta V is equal to 0. And here, delta V is less than 0. So delta V is negative. Delta V over delta T is just a negative number, and that is your acceleration here. So this is the acceleration versus time graph that corresponds to this velocity versus time graph. In general, in this class, we are going to be working with objects with constant acceleration. So the acceleration is going to be the slope of the velocity versus time graph. If this is time, if this is velocity, so the slope of this guy here, that is the acceleration. I have data here for Usain Bolt. I hope you know who he is. He just retired, and this is data from 2008. Here we have position versus time graph for a 100-meter run, and here we have acceleration, velocity versus time graph, or speed versus time for the same run. So let's see what these graphs are telling us. So he starts from 0, the position, and then you can see that there is this bending here, and then it becomes a straight line. So in this segment here, the speed is pretty much constant, right? So this is the top speed. So he reaches his top speed at about probably 3.5 seconds, and then it stays there. So let's estimate that top speed. So for that, we are going to use 2 points. We're going to take this point and maybe this point. And then we're going to calculate delta x over delta t for those 2 points. So delta x, well, this is about 80, right? 80 meters. minus this one here, which is 20 meters. So delta x is final position minus initial position, which is 80 minus 20, divided by delta t, which is final time, which is 8 seconds, minus initial time, which I'm going to say is roughly about 2.8 seconds. So that is the time here. So now I have delta x over delta t. I can do this math and I get that this is 7.99 meters per second. That is the top speed of Usain Bolt. That is the speed in this segment, which is a straight line. So now let's, to make sense of the speed, let's change it. Let's change this to miles per hour. So 7.9 meters per second, right? So remember, I'm going to multiply by 1, right? So I want to get rid of the meters now. I want this to go to miles. So I have 1 mile on top, and then I have 1609 meters. And then I'm going to multiply by 1 again to get rid of the seconds. So I'm going to have 3,600 seconds on top, and I'm going to have 1 hour at the bottom. So now these meters cancel with this, these seconds cancel with this. I keep the hours, that's what I want. And now I can do the math here, and this is roughly 17 miles per hour. That is the top speed that Usain Bolt has right there during that part of the run. So let's compare that with the speed, the velocity or speed versus time graph here. And one thing that we can do is let's estimate the acceleration right here in this segment where he starts the run before he reaches the top speed, right? So the acceleration is what? The acceleration is delta V over delta T, right? So let's take these 2 points. Let's take this point and that point there. So I'm going to say the speed at this point is 9.8 meters per second, reading from the graph here. This is roughly 9.8. And then I'm going to say the speed at this point here is roughly 5.4, right? 5.4 meters per second. So this is V final minus V initial. Then I'm going to divide by T. So I'm going to say the time there is roughly about 2.4 seconds. And the time here, I'm going to say that is roughly 0.9 seconds. So then if I do this math quickly, I'm going to get that this is 2.31. What are the units? The units are meters per second every second, or meters per second squared. So Usain Bolt has an acceleration of 2.31 meters per second every second. Compare that with a lion, which has an acceleration of 9.5 meters per second squared. He has an acceleration of 2.31 meters per second every second, and he's the fastest man on Earth. So it takes for him about 3 seconds to reach the top speed, and then he keeps that speed for about 7 seconds until he reaches the end of the 100 meters. Quick question here before finishing this video. So you have a particle that has velocity v1, and then as it moves from 1 to 2, from here to here, the acceleration is shown. So it moves from this point to this point. This is the velocity, right? This green vector here, and the acceleration is pointing upwards, right? So the acceleration is pointing against the velocity. That means this guy, the velocity of this object is going to be decreasing. He's going to be slowing down. What is the velocity vector v2 as it moves away from point 2? So what would be the next green vector that you have to draw there? Which one of these? So take a minute to answer the question. So, and the answer is B. So this vector would be way longer than this. And so that is not consistent with having an acceleration that is decreasing the speed. The speed is going to change, but it's not going to be zero. It's not going to completely turn. So the only possible answer is 2, and that is the right answer.